Okay, thanks, Dick, for the very kind introduction. And yeah, as someone who lives kind of, not too far away, I get the privilege of visiting the Simons Institute pretty frequently, so it's a pleasure to be here, having an opportunity to speak with you. And I do, at the outset, I do want to thank Dick and Alistair and the rest of the leadership for just doing such a great job for running the Institute. It's really, over the last 5 years, it's added a totally new dimension to sort of our lives as theoretical computer scientists. It's been very cool. All right, so what I want to talk to you about today is this thing I call application-specific algorithm selection. So what do I mean? Well, so let's start with what do I mean by algorithm selection? So one of the special semesters at the Institute this term is on algorithms and uncertainty. So there's a lot of people here, including myself, where our day job is basically algorithms. It's what we think about all the time. And when you do algorithms as your day job, you get used to the following scenario. Right? You're in your office, a colleague comes in, sits down, says, I was building this system, or, I was writing this software, and I realized, I have to solve problem X. And X could be any number of things. Well, say it's the traveling salesman problem or something. And they sit down and they say, you're an algorithms person. Which algorithm should I use? And this is actually a much trickier question than it might seem at first. It's a little bit like you go to a cocktail party, someone introduces you to a medical doctor, and you say, hey, doc, I've had this 100-degree fever for the past couple days. What should I do? The reason these are tricky questions in sort of the same way is that the correct answer depends on details which have not been divulged. So just like a 100-degree fever could signal different kinds of illnesses, each demanding their own specialized medical treatment, different collections of instances of a common computational problem themselves deserve their own algorithms, the algorithmic treatments. That is, while we wish, perhaps, that computational problems admitted some silver bullet algorithm, which was always the right one to use, for many of the problems that we face, this is just not true. The correct algorithm to use really depends on the relevant inputs. So, if you want to just get the person out of your office, just like the doctor might say, well, take 2 Advil and call me in the morning if it doesn't work, I might be tempted to say, try local search and call me in the morning if it doesn't work. But so that's the key point from this slide. It's just that the correct, it's a simple point, but it's fundamental for this talk. The right algorithm for solving a problem depends on the instances that you care about. Okay? Here's maybe an example picture that I just want you to have in mind, sort of to visualize this point. So this is a paper by Smith-Miles et al. On graph coloring. I could have picked any number of other papers from empirical algorithmics to make the same point. So what Smith-Miles did is they scoured the literature to find all of the sort of hard benchmarks of graph coloring instances that people had looked at. And also they found out what all of the state-of-the-art heuristics were for solving graph coloring. And what they did is they just ran all of these graph coloring heuristics on all of these benchmark instances to try to get some understanding of which algorithm did better on which kinds of instances. Okay? So they plotted all the instances on a plane. Okay, so they figured out some way to embed graph coloring instances onto the plane. And using their training data, they used machine learning to estimate a prediction function, which, as a function of where you are in the instance space, predicts which of these 7 algorithms is going to be the fastest one. Okay? And the only thing I want you to notice about this picture is that all of the colors are fully accounted for. Okay? We have 7 different algorithms, and each one has its own sort of domain of superiority. Okay? So implicit in an analysis like this is saying, well, if you want to solve graph coloring, first, figure out where in this space your typical instances lie, and then the color coding gives you a suggestion of what kind of algorithm to use. Okay? So this is the picture I want you to have in mind. So what I want to do next is I want to talk about 3 examples which serve to both motivate and provide interpretations for the sort of general theory I want to tell you about in the second half of the talk. And I just remembered, I forgot to say at the outset, the meat of the talk in the second half, that's all joint work with Rishi Gupta, who's in the back, my most recently graduated PhD student. Okay? So 3 examples. All of them have connections to the Simons Institute, which I'll mention as we go along. Okay? So first I want to talk about something called SATzilla. So you may have heard that there are these things called SAT competitions. Okay? So every other year, all the people who like to nerd out about satisfiability, they get together. You get to submit any SAT solver you want. And the people who run the tournament will run your solver on all kinds of different instances. Random instances, industrial instances, and so on. and they see which solvers do the best, and they give out medals. Okay? So this is a thing. It's been going on for a while. So a team at University of British Columbia, including Kevin Leighton Brown, who's one of the long-term visitors this semester in the Algorithms and Uncertainty program. He was also here last fall. So this UBC group had a bold, even I would say maybe slightly cheeky idea. They said, you know, I'll bet it would be fun to win a SAT competition. But I don't really want to write a solver. That sounds like a lot of work. So they brainstormed about how maybe they could win a competition without actually writing a solver from scratch. And they thought about the following idea. They said, well, let's look at the solvers that won a lot of medals last time, 2 years ago, at least the ones that are open source. And they ran those solvers on a bunch of instances, and they noticed that they had wildly different running time performances. So some instances, one algorithm would be really fast, another one would be really slow. Some other instance, they'd be flipped. So you'd see a picture much like the one on the previous slide, where different SAT solvers simply did better on different kinds of instances. So the idea was, well, you know, let's just maintain a portfolio of these SAT solvers. And when we are given a new instance, what we do is we just figure out which of the 7 SAT solvers is most likely to run the fastest, and then we'll just run that as a black box. Okay? So there's no new solver except in as much as there's this meta-algorithm picking which of these solvers to use when confronted with a new SAT formula. Okay? So a little more detail. So again, they had 7 SAT solvers in their portfolio. And then, you know, they identified a bunch of features of SAT instances, of formulas. So some of the features were kind of obvious ones, like the variable to clause ratio. Some of them were not so obvious, like Knuth's unbiased estimator for the search tree size. Or one thing which turned out to be super useful was to just do local search for like a second and see how far you got, and use that as one of your features of a SAT instance. But in any case, they defined hundreds of features of SAT formulas. And then when they again used a machine learning approach to, separately for each of the 7 solvers, learn a prediction function. Okay? So for solver number 1, there was some prediction function, which when you feed in the features of a given instance, would predict for you what it thought the running time of that SAT solver would be. Okay? So you have 7 of these prediction functions. They called them empirical performance models, EPMs. Now, once you've learned good EPMs for your 7 solvers, it's pretty clear what your meta-algorithm is. You're given an input, compute the features, see what the 7 EPMs say, and run the solver which runs the fastest. And that's basically what they did. That's basically SATzilla. And it basically crushed the competition in a couple competitions in a row, to the point that now actually, you know, these portfolio algorithms are explicitly disallowed in most of these SAT competitions. Okay. All right, so that's the first example, just totally on the empirical side. Okay? Again, to motivate the theory I'm going to present later. So the second example, so this draws more on the connections between computer science and economics that Dick alluded to. So this is about a really high-stakes application which is happening right now, as we speak. Okay? So it's an auction being run by the FCC, the so-called incentive auction. It started on March 29th of this year, and it's still going now. Okay? So it's an auction that proceeds over a long period of time. And you know, if it surprises you to hear that the FCC is running an auction, actually they've been running auctions for a long time, since the early 90s. So whenever they wanted to sort of, you know, sell some new wireless spectrum licenses for people to, you know, build out new technologies, they would run an auction. So companies like Verizon or AT&T would bid in an auction, you know, competing for, you know, who gets which licenses for the wireless spectrum. So that's an old idea. But there's something new which is happening this time for the first time ever. And the reason things are different now than they were ever before is that the really juicy part of the spectrum is now pretty much all accounted for. It's all already owned by somebody. So if you want to grant somebody new wireless spectrum, you have no choice but to take it away from someone else. And that's actually exactly the point of this auction which is running as we speak. So it has 2 phases. It's a double auction. There's a reverse phase and a forward phase. So a forward auction, that's just like when you put something on eBay. Okay, so when you're selling stuff, you're running a forward auction. On the other hand, if you go out for bids for contractors to, you know, renovate your house or whatever, that's a reverse auction. That's where you're using an auction-type format to actually purchase something. So this has a reverse phase and then a forward phase. The reverse phase, the government has to actually get some licenses, take them away from other people. The other people here are going to be television broadcasters. So that's the reverse phase, buy back licenses from people who don't have much value for them. The second phase of the forward auction is you turn around and you sell them back to, presumably telecom companies like Verizon and so on. Okay? So it's really meant to transfer licenses from broadcasters who are thought to be deriving low value from them to, companies that can really build out new wireless broadband technologies. You'll notice the numbers here are pretty big. So the government is hoping to make something like $20+ billion net profit from this auction, which is then supposed to be used to reduce the deficit. And indeed, this was a very, so to run this auction, the FCC needed congressional approval. They had to pass a bill authorizing the FCC to do this. So this was one of those rare bills in like 2012, which actually had bipartisan support and just passed quite easily. And indeed, they even called it the Middle Class Tax Relief and Job Creation Act. I mean, who's going to vote against that, right? Okay, so that's the high-level idea. And again, the forward auction has been around for close to 25 years. The reverse auction is totally new. So let me drill down a little bit more on the reverse auction. Okay? So the format for the reverse auction was proposed by two economist colleagues of mine at Stanford, Paul Milgram and Ilya Segal. We had Paul Milgram at the Institute several times last fall, when we had a special program on economics and computation. He actually gave an open lecture in this room kind of almost exactly a year ago on exactly this topic, on the incentive auction. So they proposed how to do it, and this is the one that got adopted. And what's really cool is, all right, so fundamentally, what problem does the reverse auction have to solve? It has to figure out which of the television stations stay on the air and which ones get kicked off the air. Okay, that's what you're trying to figure out. And the Milgram-Segal format really says, do whatever you want as long as you use a greedy algorithm. Okay? Now, why were two economists caring about greedy algorithms? It's because they turn out to have really nice economic properties. So it turns out if you use a greedy algorithm to solve the underlying computational problem, it admits sort of a very nice implementation, what's called a descending clock implementation, which is really kind of a pleasure to participate in. Okay, so it's very easy for the participants. So that's why they focused on greedy algorithms. So what kind of greedy algorithm should we use? And again, don't forget the problem. We have all these television stations. They're currently on the air. We want to leave a small subset of them on the air and buy everyone else out. Okay? Kick everyone else out the air. So it's a greedy algorithm for picking who stays on the air. All right, so greedy algorithms, you all know how they work. You usually do a one pass over the objects, according to some ranking, and then you make an irrevocable decision each time you consider an object about whether to include it or exclude it. So what order should one consider the stations in? Well, so the first thing, on the good side, so stations with higher value for their license, that is less willingness to accept a certain offer. So stations with high value for their license should be prioritized for staying on the air. Right? That just makes sense. The people who want it more should be toward the front of the line of being on the air. So that you could just consider the value. That would be a totally reasonable greedy algorithm. But there's at least one other thing which might be worth considering, which has to do with television stations conflicting with each other. So as you can imagine, if you have two different television stations and their broadcasting areas overlap, they can't both broadcast on the same channel. Okay, then you'd get sort of bad interference in a significant part of both of their neighborhoods. So anyone you conflict with, i.e. your broadcasting region overlaps with, they cannot be on the same channel as you. Okay? So what does that mean? That means actually, if some station conflicts with lots of other people, you may be less inclined to keep them on the air because they impose so many other constraints on who else you could keep on the air. So more conflicts is bad. So you could also discriminate against television stations who overlap with lots of other neighboring stations. Okay? So those are the two criteria they decided to focus on in the greedy algorithm, which actually got implemented. And so given two criteria like this, there's many ways to combine them into a scoring rule. The scoring rule which was implemented is to first order this one. Okay, so higher rank is better. So this is a greedy score with higher numbers being better for the station. So it's linearly increasing in the value of that station, and then it decreases with the inverse square root of the number of conflicts. Okay? And so this is literally the formula that's in the auction being run right now. Okay, it's not just made up. People definitely argued about this 1/2 quite a bit. Like, what's up with this exponent? Does this make any sense? Doesn't this seem kind of weird? There is some theoretical precursors to this square root rule, specifically a paper by Lehman O'Callaghan and Shoem on combinatorial auctions, where they're basically using a similar greedy algorithm in a slightly different context. My understanding is that the reason Milgram and Segal proposed this rule is because they tried lots of rules like this. In particular, they tried lots of different exponents. And on synthetic data that they deemed representative, exponents pretty close to 0.5 seemed to be the sweet spot. Okay, so that was, as my understanding, the primary consideration for why they settled on this exponent of 1/2 experiments with synthetic data. Okay, so this activity of figuring out, what should that exponent be and why 1/2 and doing it from data, I mean, this should remind you of something that, at least if your machine learning friends are like my machine learning friends, something that, some of your friends are doing all day long every single day, namely parameter tuning, or if you like, hyperparameter optimization. So this has many forms. So I'm just pointing out an analogy. So, what we just did is basically a parameter tuning problem, of which there are many more across computer science. So these days, you hear mostly about machine learning, even just gradient descent. Something as simple as gradient descent, you got to choose a step size. And it's kind of a dark art, how you choose the right step size. Okay, you do it by trial and error for the most part. Things can get even hairier with hyperparameters, like if you're doing regularized regression, you have to figure out, what's the coefficient for the regularization term. Again, typically, you use trial and error kind of heuristics for figuring that out. Okay. Parameter optimization is certainly not unique to machine learning. So one example I like is Cplex. So Cplex is a well-known commercial solver for linear programs and integer programs. And maybe at first you're like, oh, a linear programming algorithm. We think of it as some fixed algorithm. Oh, it's just simplex or whatever. Actually, Cplex is really a meta-algorithm parameterized by many, many parameters, 135 parameters, in fact. Okay? So for any instantiation of those parameters, you get n algorithm. Right? But Cplex itself is this family over all possible parameter choices. So there's a 221-page reference manual, sort of a guide to these parameters. And if you're thinking, wow, with 200 plus pages, there must be some really sage advice about how I should think about the parameters, think again. Pretty much all they have to say is, you may need to experiment. Thanks, Cplex. Right. Okay, so I mentioned this slide because, these types of parameter tunings, there's also something I kind of have in the back of my mind once we get to the theoretical development a little bit later. Okay. All right, so the last example I wanted to give, this is now sort of on the purely theoretical side. I think you could implement what's in these papers, but I don't think they have been implemented. So this is a sort of small but very nice literature on self-improving algorithms. And the person who's been really the consistent contributor in self-improving algorithms is Seshadri. He's also a long-term participant in the Algorithms and Uncertainty semester this term. So what is it? So what's the model? So the model is, consider a problem like sorting. Okay? So you're going to see instances of the problem, so like arrays to sort, in a sequence. And they're not going to be adversarially chosen. They're going to be drawn from some distribution which you are not privy to. Okay? So the first array you see, you have no idea what it's coming from. You just want to use merge sort, whatever. But then you start seeing more and more arrays, and it's conceivable you'd notice patterns in the kinds of instances that you're seeing. Now, when you're sorting, you could always just use, say, merge sort, and it would be n log n worst case time. But actually, if you assume something about the distribution of the inputs, there's many cases where you can beat n log n time, indeed even get sort of expected linear time. Okay? So if you're in one of these lucky cases where the data has the structure that you can beat merge sort, you'd like to recognize that automatically, and ideally sort as quickly as the information theoretic optimal algorithm for the distribution. Okay? And so the focus in these papers is mostly on just making sure you don't use too much bookkeeping. So it'll be a little bit different from our focus. But still, this is very much going to be in the spirit of the theory I'm going to tell you about today. Okay, self-improving algorithms. Okay, so those are the three examples I wanted to cover of how. So remember where we were. What is algorithm selection? And we sort of looked around and looked for some case studies of how do people actually do algorithm selection. And so we saw SATzilla, which is this idea that you choose an algorithm from a portfolio on the fly as a function of the instance features. We saw the FCC auction example, which is basically kind of a parameter tuning problem, figuring out what should be the right exponent. And then we noticed there's lots of other parameter tuning problems in the world also. And then this third one of self-improving algorithms where inputs are coming in from a distribution and you want to do almost as well as if you knew the distribution. Okay? So those are the three examples we saw. And so now, and so I've been, a big fan of all of these works for a long time. And for many years I was wondering, what would, appropriate theory look like to help one think about what's happening in this way of using algorithms, these types of algorithm applications? So this talk is sort of the best answer I've come up with to date, about what is the theory which most closely mirrors these types of case studies. So what's it going to look like? What should a theory look like? Well, I guess the first thing I want to point out is it's not going to look like the way analysis is usually done in the theoretical analysis of algorithms. So usually, in theoretical analysis, we look at worst-case analysis, and I'm going to argue that that's inappropriate for what we're trying to capture here. So what do I mean by worst-case analysis? So you're trying to basically summarize a very complicated object, which is the performance profile of an algorithm, right? So notice when you say the performance of an algorithm, this is actually kind of a complex object, right? So it's really a vector, in effect, of, say, the running time or the solution quality of this algorithm on every possible input you might ever run it on. Okay? That's sort of, in its, grandly the performance of an algorithm. Now, to reason about algorithms, you usually want some kind of summary statistic. You're like, let me just think about, sort of one number so that I can compare algorithms in a clean way. And worst-case analysis just says, use the summary statistic of the worst the algorithm ever does on any input, possibly parameterized by the input size, something like that. Okay? Now, worst-case analysis has served the study of algorithms very, very well. When I teach undergraduate algorithms, pretty much everything I do in the class is worst-case analysis. And so let's review, what do I tell the undergrads? Why are we doing it? Well, so, first of all, the best-case scenario is kind of utopia, right? When you can prove a positive result that's true even in the worst case, you basically can put the problem to rest. Okay? You basically never think again about how to solve it. Whatever the input is, you don't care. You have a guarantee that you're happy with. Secondly, despite the fact it's such a strong positive guarantee, there are tons of killer applications. So specifically, undergraduate algorithms is basically a parade of killer applications of worst-case analysis. Right? I'm thinking like, Dijkstra's algorithm implemented with heaps or something like this. It has a super fast theoretical running time. It's also a super practical algorithm that you'd really want to use. Okay, but there's also some well-known drawbacks to worst-case analysis. So let me just remind you of these. So obviously, if it's going to be incorrect, okay, if it's going to give you bad advice, it's going to stem from the fact that it's too pessimistic. Okay, that this could be governed by performance on inputs which will never show up. Okay? And that can actually lead to flat-out bad advice from worst-case analysis. So perhaps the most famous example is linear programming and the simplex method. So theoretically, in the worst case, the simplex method requires an exponential number of iterations to compute an optimal solution, but it's almost impossible to find instances where you see anything like that. The typical performance of the simplex method in practice is much closer to linear in the input size. Forget about exponential. So in effect, worst-case analysis is telling you don't use the simplex method, use some other method which has a polynomial time worst-case guarantee, but that's really just not very good advice. Right? So in practice, you actually do want to use simplex most of the time. So that's a problem. I stated the fact that there is no data model as a pro of worst-case analysis. Right? So when you have positive results, you're happy you never made any assumptions about the data, but you can also think about that being its Achilles heel. Okay? So there's no data model in worst-case analysis, or if there is a data model, it's the Murphy's Law data model. Okay, so Murphy's Law says whatever goes wrong will go wrong. Worst-case analysis says whatever algorithm you pick, the worst input for that algorithm is the one that's going to show up, is the one that's the most relevant. Okay? So the input that you care about actually depends on the algorithm that you use, which, outside of maybe some cryptographic applications, I claim is just sort of a paranoid and incoherent way to think about the world. Okay? All right, so we want to get away from worst-case analysis. Again, remember our thesis at the beginning. The right algorithm to use depends on the instances that you care about, the relevant inputs. So we need some notion of relevant inputs. That means we're going to have some kind of at least weak data model. All right, so it's not going to look like traditional worst-case analysis of algorithms, but it will resemble a different part of theory which is very well understood, which is learning theory. So the proposal is going to be to think about application-specific algorithm selection as a learning problem. So normally in learning, you think about things like prediction functions or classification. So maybe you think about things like half spaces or decision trees. So here, instead of half spaces or decision trees, we're going to be thinking about algorithms. So algorithms will correspond to what are normally called hypotheses or concepts on the learning theory side. In learning theory, you usually think of a loss function, which says as a function of what the correct answer is and what your guess was, what penalty do you suffer. The analog of the loss function here is just going to be the algorithm performance, like, say, the running time. And what I'm going to try to convince you is that two of the dominant paradigms in learning theory, both the kind of offline or batch learning model, in addition to the online or regret minimization model, very naturally model this problem of algorithm-specific, application-specific algorithm selection. Okay? So that's the plan for the rest of the talk. Any questions? Feel free to interrupt whenever you want, of course. Okay. All right. So let me actually tell you a little bit about the formalism and the types of things one can prove in this formalism. So I'm going to talk mostly about the offline or batch model. So let me tell you what I mean by that. So first of all, in the very first line, we're going to see a departure from the usual way you think about algorithms in worst-case analysis. So the first ingredient to the model is a set of algorithms. What do I have in mind? For example, it could be a set of 7 SAT solvers or 7 graph coloring heuristics. Or it could be a greedy heuristic, all greedy heuristics for that auction problem for some exponent possibly different than 1/2. Okay? So that's what I have in mind by a class of algorithms. So you have committed up front to use one of these algorithms, but you haven't committed to which one. And again, remember our tenet. The whole point here is that the right algorithm to use should depend on the instances. So that's why we're at no point will we advocate a single algorithm until we specify the data model. Okay. So like I said, we need an analog to a loss function. So I'm just going to denote this by cost. So A here is an algorithm, Z here is an input, and this is whatever performance measure we've decided to care about. So this could be, for example, the running time of A on Z. Maybe it's an NP-hard problem and this is a heuristic, then that could be the quality of the solution output by A on Z, or its approximation ratio, and so on. Okay? So you have a performance measure. I'm going to assume it's bounded between 0 and capital H. Okay? So capital H is how big this performance measure can get. So for example, the maximum running time before you just go ahead and time out. What we're going to want to do is think about algorithms as a real valued function. Okay? So what's the domain? What's the range? So the domain is just the input. Okay? So think of that. We've fixed a computational problem. We've fixed an algorithm for that computational problem. Now we can think of the mapping from inputs of that computational problem to the performance of this algorithm A on this input. Okay? So we think of algorithms as real valued functions, mapping inputs to performance. All right? I know that probably sounds a little abstract, so let me make it much more concrete and sort of tell you about a specific family of algorithms which I'm going to use as a running example for the rest of the talk. Most of the results are more general, but this is a very good one to just keep in mind. So think about the independent set problem. Okay, so in the independent set problem, you have a graph. An independent set is a subset of the vertices so that no two vertices are adjacent. Okay, so adjacent vertices are disallowed in an independent set. Vertices also have weights. That's what these labels mean. So these are the weights of the vertices. In this problem, the goal is to compute the independent set with the maximum total weight. Okay? It's a well-known NP-hard problem. But we're going to look at greedy heuristics for this NP-hard problem. Okay? Maybe the first greedy algorithm you'd think about would just be like, okay, well, we want a large weight independent set, so let's just start with the biggest weight vertex. Let's go ahead and greedily put that in our independent set. Given that we've done that, we can't put any of these 3 vertices in our independent set. So in the next step of the greedy algorithm, we just take the only other vertex we can, the 2, okay, for a total of 6. That's not the only greedy algorithm you could use. Another one that you see a lot in the literature is weight divided by 1 plus the degree of a vertex. Why? Well, this is sort of like a bang per buck ratio. When you remove a vertex V, when you put that in the independent set, you're also excluding from future consideration all of its neighbors, its degree of V neighbors. So you've basically ripped out of the graph 1 plus degree of V vertices, and you earned WV units in your objective function. So this is the bang per buck per vertex removed. So that's another natural thing to maximize. Now in this particular graph, the algorithm does something different and actually computes an optimal solution. So in this case, because this is a high weight and only has degree 1, that's going to get picked first. The other isolated node will get picked second. Now this is blocked and this is blocked. This is not blocked. So it concludes with this vertex. Okay? So we changed the greedy rule, and we saw we got a different answer. In this case, the second algorithm was optimal. It would be very easy to come up with examples where this algorithm is suboptimal and the first algorithm would be optimal. Okay, so which algorithm is better just really depends on the graph that you're looking at. You might see a resemblance between weighted independent set and the auction example that we were talking about earlier. So remember, then we were talking about basically keeping stations on the air, and stations could interfere with each other. So there's a clear abstraction here where basically vertices correspond to stations and edges correspond to conflicts. So this is the same kind of problem that was being studied in the auction problem. And you could also imagine a square root rule here as well. Okay? And again, a priori, there is no reason to think, there's no reason to know why one of these particular greedy algorithms would be better for your application than another one. Okay, so what's an example of a class of algorithms? Well, let's just, here's like the first thing we could try. And again, the results will be much more general. But just think about this class. Suppose we just interpolate between the two greedy algorithms I just showed you. The one that orders by value and the one that orders by value over 1 plus degree. So one way to interpolate is we'll look at only greedy algorithms that use the ratio between the weights and 1 plus the degree raised to some power. Okay, where p could be 0, could be 1. That recovers the two examples so far. Could be 1/2. That's in the spirit of the auction solution, or anything else. Okay? So for each choice of p, we have one greedy algorithm. Varying over all choices of p, we have an infinite set of greedy algorithms. Okay? All right. So I hope you have a better feel for what I mean by a class of algorithms at this point. So let me tell you about the rest of the model. Okay? And if you're familiar with pack learning, it's basically the same as a pack learning model. So also in the spirit of the self-improving algorithms discussion, we will commit to the fact that inputs are drawn from a distribution. Okay? So this is a departure from worst-case analysis. Before you've chosen an algorithm, I've committed to a distribution over inputs. All right? So that's sort of a coherent way of thinking about which inputs you care about. All right. So call that F, that distribution. Now, the algorithm designer will not be privy directly to this input distribution. Okay? That would be too easy and maybe too unrealistic. Rather, the algorithm designer has benchmark instances, benchmark data sets, which we interpret as IID samples from this unknown distribution over inputs. Okay? So knowing the distribution only in as much as you know S samples from the distribution, your job is then to commit to an algorithm from this class, like a value of p, that you will then use forevermore on instances that are also drawn IID from the same distribution F. Okay? So it's called batch learning because I give you all of these S samples at once in a batch. You process them as long as you want. As a function only of the samples, you figure out which algorithm from your class you're going to run on future instances. Okay? You may be tempted to sort of, if you remember the SATzilla example at the beginning, you may be tempted to remember, well, didn't we have that example where we were more ambitious? And actually, we didn't just commit once and for all to an algorithm forevermore. Rather, we had a mapping from input features to algorithms. That fits just fine in the same formalism. Right? So you can optimize over mappings from instance features to algorithms rather than just optimizing over algorithms as well. Okay? All right, so what's the benchmark? What does it mean that you solve this problem? Well, given that you're restricting to an algorithm from C, the best thing you can do is do as well as the best algorithm in this class. Okay, so the goal is to find some algorithm in the class, ideally A star, that approximately optimizes the expected performance, where this expectation is with respect to the input distribution, which of course you don't know. Okay? So that's the goal in the batch learning model. Is that clear? Okay. So what might we hope to prove? Well, we could look to just classical learning theory. Again, this is a totally standard setup, and say, what kind of nice rules of thumb are there on the learning theory side? And something you learn, in chapter 2, if not chapter 1, is that the sample complexity, so the data requirements needed to learn a good classification rule or a good prediction function, scales with how complex the set of prediction functions or classification rules you're looking at. Okay, so the more complex set of hypotheses you're willing to consider, the more data is required. So, so for those of you who know the VC dimension, this is the kind of thing I'm talking about. And as a corollary of this, you get on the learning theory side that as long as you're only interested in learning the best simple function, or the best simple classifier, the data requirements are quite modest. So what we might hope for algorithm selection would be an analogous rule, saying as long as your class of algorithms involves only simple algorithms, whatever that means, then you should be able to learn over that family from a modest amount of data. That's the kind of theorems I'm going to be aspiring toward. Okay. So to do that, we need to commit to what we mean by a class of algorithms being simple or not simple. Okay. So the good news is we do not need a new definition for this purpose. We can just use sort of off the shelf a classical definition from statistical learning theory, which is known as the pseudodimension. I will give you a definition of the pseudodimension, but I'm not going to do it for a couple slides. Okay? For a couple of slides, I want to tell you why maybe you should care about seeing the definition of the pseudodimension. Okay? But so this is what's going to work for us. All right? So what do we want from this definition? Well, what do you want from any definition? Right? On the one hand, right, to convince you that a definition is interesting, I should convince you, first of all, that there's interesting implications if you meet the definition. Okay, so we're going to see that. We're going to see that if you meet the definition, then you have low sample complexity for learning the best algorithm from a class. Secondly, you better have some juicy examples. Okay? Examples you care about that actually meet the definition. So then we'll talk about for families of algorithms like greedy algorithms, what actually is the pseudodimension. Okay? All right, so first the implications. So suppose I tell you that a family of algorithms has low pseudodimension, is simple in that sense. What does that buy you? Well, then you immediately know that the sample complexity is reasonable. Specifically, what I want you to focus on, so this is the sample complexity here. What I want you to focus is on the linear dependence on D. Okay? So the pseudodimension, whatever it is, it's governing the sample complexity. Okay? So if D is small, the sample complexity is going to be small. If D is big, the sample complexity is going to be big. Okay? What are the other parameters? So H, you might recall I was assuming that performance values range between 0 and H, so that's sort of the spread of possible values we're thinking about. And epsilon is the additive error you're willing to tolerate. Okay? So the goal really is to just output an algorithm whose expected performance is within epsilon of the best algorithm of your class. Okay? So it shouldn't be surprising to see some dependence on this ratio H over epsilon, the spread over the error required. And the interesting part is the linear dependence on D. So the guarantee, this is what the guarantee says. If your class of algorithms has pseudodimension D and you have this many samples, then that's enough samples to learn the best algorithm from that class. Okay? How do you do it? Well, if nothing else, you can just use brute force search. Okay? You can look for smarter algorithms, but if nothing else, here's how you use brute force search. You have your samples. You just see which of your algorithms does the best on your samples, and then you just use that forevermore. And the guarantee is that the algorithm that you choose, which was optimized for the data, will be within epsilon, with high probability, will be within epsilon of the best algorithm from that class. Okay? But again, high-level point, pseudodimension, if it's low, whatever it means. If it's low, sample complexity is also low. All right, so so far that's totally classic stuff. So now the question is, are there any interesting examples of this dimension, of the pseudodimension being low? So, for example, greedy algorithms. What can you say about the pseudodimension? Well, I haven't told you the definition, so it wouldn't be fair to ask you. But even if you knew the definition, it's not totally clear a priori. In fact, I still remember, a couple times I told a couple of friends of mine that, I was busy computing, effectively the VC dimension of greedy algorithms, and they looked at me like I had lost my mind. You could tell this did not type check. Like, VC dimension, greedy algorithms, what are you talking about? But it makes sense, and you get nice results. Okay? So just a sanity check. So for finite sets, that's not a very interesting case. So just by elementary arguments, you get a pseudodimension of log of the size. So whenever you just have like 7 algorithms or something, this is a very low sample requirement. Much more interesting, and what I'll focus on is greedy algorithms. Okay, so they're going to be greedy algorithms with 1 parameter, like the examples I've shown you thus far. And the pseudodimension is only logarithmic in n, where n here is the size of the instances that you're getting from the distribution. So for example, an independent set, n would be the number of vertices in the graph. All right? So the pseudodimension is only logarithmic in the input size, which again, as we saw, means the sample complexity will also be only logarithmic in the input size. And it's definitely not just, so, not all classes of algorithms have low pseudodimension. I mean, it does differentiate. So sufficiently complicated classes of algorithms can have unbounded pseudodimension. But this is robust in the sense that lots of other types of algorithms also have low pseudodimension. So if you do local search, you get some kind of dependence on log of the neighborhood size, but otherwise log n. In the self-improving sorting work that I mentioned, they in effect identify a subcollection of sorting algorithms, which are always guaranteed to be near optimal, which has pseudodimension basically linear in the input size. And if you want to do the SATzilla application, where you more generally learn the best mapping from input features to algorithms, then you just suffer a linear dependence on the number of features that you're using. Okay? So the sample complexity remains small for these as long as each algorithm itself has small pseudodimension. Okay? All right, so those are the 2 things that I wanted to promise you. First of all, if you meet the definition, automatically get cool consequences. Secondly, actually, the motivating examples do satisfy the definition. All right, so because this plays a starring role in these results, let me actually tell you the definition, although if the slide doesn't make sense, don't worry about it. Okay, you won't need this again. So for those of you that know VC dimension, it's really just the real valued analog. Right? So why is VC dimension not quite what we're looking for? So VC dimension is a measure of complexity of binary functions, 0-1 functions. We have real valued functions. Okay, how do you turn a real valued function into a binary function? You just threshold it. Okay? Is it above or below a given threshold? That's literally it. That's the pseudodimension. So there's still a notion of a set being shattered, meaning you exhibit all possible different labelings of that set. The only trick is now you get to pick whatever thresholds you want. Okay, so to shatter a set, S, you pick your favorite set of thresholds, 1 for each point in the set. And it should be the case that for every subset of the set that you're shattering, you can find a function which is above the thresholds on the prescribed set and below the thresholds outside the prescribed set. Okay? So really you're just saying you want all possible different behaviors to arise as you range over all of the algorithms in your class. Okay? And then the pseudodimension is just the biggest set size that you can shatter. Now, if this seems like a mouthful, that's fine. I mean, if it's the first time you've seen it, it is a mouthful for sure. So the one thing I want you to take away from this is, despite the fact there's a lot of words, it's actually really not very hard to prove bounds, good bounds, on the pseudodimension for things we care about. So let me prove this point by just giving you a sketch for our running example. So let's imagine, so it extends to sort of general greedy algorithms, but let's just focus on those weighted independent set greedy algorithms we were looking at before. Okay, so remember, this is just a family of algorithms parameterized by p. This is specifying how you trade off the weight with a degree. Okay? So the claim is that the pseudodimension of this family of algorithms is only logarithmic in the number of vertices. Okay? What does that mean? That means we can only shatter subsets up to size log n. Okay, we can't shatter anything bigger. That's what it means to have log n pseudodimension. So let's see why that's true. Okay? So fix a set of inputs. Right? So this contains S things. Each one is a graph with weights on it. Okay? So we have S graphs with weights. Now, there's an infinite number of algorithms, but you're not going to see an infinite number of distinct executions on this finite set of samples. Okay? So call 2 choices of the exponent p and q equivalent if on literally every input in this sample, the algorithms run in lockstep identically. Okay? Meaning they pick exactly, they consider the vertices in exactly the same order. Okay? So that's what it means for 2 different choices of an exponent to be equivalent with respect to the sample. Okay? So if I don't fix the sample up front, if I just pick 2 exponents, I can always find an instance of the weighted independent set where they do different things. But if you fix the sample first, then often nearby p's and q's will have exactly the same execution on all of the inputs in that sample. Okay? So the lemma that we need is that the number of equivalence classes can only grow polynomially with the size of the instances n and the number of samples little s. Why is that enough? Well, remember the definition of shattering says you need to exhibit 2 to the s different behaviors, okay, to get all 2 to the s different possible labelings. So if you really only have, poly and n and s distinct algorithms at your disposal, you can only get this many different behaviors for s up to log n. Okay, so the theorem reduces to this lemma here. Number of equivalence classes only grows polynomially with n and s. So let me just give you the idea for this. So fix the sample size again. It has size s. How do we use it? It's a greedy algorithm. Okay, so here's how we use it. The greedy algorithm's execution depends only on how various comparisons get resolved over the course of the algorithm. Okay, so one of these greedy algorithms for the weighted independence set problem, what is it going to do? It's going to compare, the weights over the degree to some power to the weight over the degree to some power between 2 different vertices v and x. Okay? Maybe v wins, maybe x wins. Okay, who knows? But the point is, if you tell me the results of all comparisons of this form, I know exactly what your algorithm is going to do. Okay, so the results of the comparisons fix the entire trajectory of the greedy algorithm. So that's an important point. The second thing we use, so where's the single parameter property? So this is where we use the greedy algorithm. Where do we use the single parameter property? Well, the claim is that for a given potential comparison, like say the vertex v versus the vertex x, as you range over all algorithms, i.e. as you range over values of p, let's say starting from 0 and going to infinity, the result of this comparison will flip at most once as you start p at 0 and go all the way out to infinity. Okay, so it may be that when p is 0, this thing has a bigger weight. So maybe this is bigger than this when p is 0. That's going to remain true for a while. But then at some value of p, who knows, 3, whatever, it's going to flip the other way. And this side will be bigger than this side. But then the claim is for all larger p, this side will continue to be bigger. So you have one interval where this is the winner of the comparison, and a second interval where this is the winner of the comparison. Okay? So for a fixed possible comparison, there's exactly one threshold exponent where the result of that comparison switches. Now, there aren't that many relevant comparisons, right? So the number of relevant comparisons, you just have one for each pair of vertices and each possible degree that they might have. And that's a polynomial and an s number of comparisons you need to care about. And so that says, if the number of comparisons is only this, it says there's only a polynomial number of thresholds. Okay, so values of p where the execution of the greedy algorithm differs at p minus epsilon versus p plus epsilon. That only happens a polynomial number of times, so you only have a polynomial number of different equivalence classes. Okay. All right. So just a quick summary from the batch model. So again, there's a pseudodimension definition. If you don't have to remember the definition, but remember that it's not that hard to bound it. Lots of algorithm classes we care about. It's small, and it automatically gives you sample complexity results. Also, I'm not really talking much about running time, and indeed that's largely an open question, but you can implement these learning algorithms at least in time only exponential in the pseudodimension. So when the pseudodimension is this small, you actually get a polynomial time algorithm for learning the best algorithm from data also. Okay, so let me just do 2 more slides and then I'll wrap up. So after we talked about the auction problem and sort of trying to choose that 1/2 exponent, we mentioned how we can think of that as just sort of a version of parameter tuning, which is being done all over the place, especially in machine learning. So I just want to mention one result that we have, which, it's sort of a baby step, but I hope it's a teaser. I hope it motivates more general results about hyperparameter optimization. So this result's about gradient descent, choosing parameters in gradient descent. And there's actually 3 things you might need to choose in gradient descent. Where do you start? What is your stopping criterion? What error are you willing to tolerate? But most interestingly, third, the step size. Okay, so how far do you go in the direction of the gradient in each step? So that's what people really worry about the most. So suppose you look up a textbook on convex optimization. What does it tell you about choosing the step size? Does it give you any guidance? Well, it does. So for example, if you have a strongly convex function, basically the textbook will tell you, it'll say as long as your step size is below this threshold, so as long as your step size is sufficiently small, you're guaranteed to terminate in some number of iterations close to the global minimum. And it gives you the formula as a function of how strongly convex it is of exactly, what's this threshold on the step size. But, in practice, this is super conservative, right? So this is the step size which actually gets you the theoretical guarantee. In practice, you almost always use a much bigger step size. You run the risk of overshooting, but typically you'll get there in much fewer iterations. Okay? So the goal here was so what we had in mind was someone trying to understand the best step size in this convex regime where they were being overly aggressive with the step size. And again, you can prove similar kinds of sample complexity results. So now we're thinking about a distribution really over convex functions and starting points, and you're trying to figure out the step size which minimizes the expected number of iterations before convergence. And that, again, can be analyzed using slightly different techniques, but it's still very tractable analysis. OK, so I don't have time for the online model. Let me just say what it is. So I told you about the batch model, which the two characteristics of the batch model are there's an unknown distribution, and I give you a whole bunch of samples at once from that unknown distribution. The online model differs in two respects. The first is that it's distribution-free. It's prior-free. So it actually has a worst-case flavor to it. An adversary will pick for you a, for example, weighted graph at each time step. The second difference, as would suggest, it's online, meaning I don't give you a whole bunch of samples as a batch up front. Rather, I unveil to you inputs one by one. And on each day, you have to decide on an algorithm before seeing the input on that day. The goal then is to figure out the right algorithm to use or the right parameter settings, which is almost as good as the best algorithm or best parameter settings in hindsight. Okay, so you can also get results in the online model. Rishi is actually giving a talk on exactly this, on the details of the online model, at the next workshop in the Algorithms and Uncertainty semester, which is the third week of November. So for those of you that are around, I definitely encourage you to check it out, because I think Rishi proved some quite cool things about this model. So let me just wrap up with a couple open questions. So as I said, I really have not addressed computational complexity issues. This was all just about information theoretic results, sample complexity bounds, how much data, at least in principle, is necessary to identify the best algorithm from a class. We've been thinking about this. We've been thinking about non-trivial learning algorithms. It seems like a worthy challenge problem. So it would be great to have some examples where you can beat brute force search. I think there must be at least some isolated examples out there. I suspect there's a fair amount of work to do doing complexity theory saying you can't beat brute force search for a lot of these learning type problems under suitable complexity assumptions. So I think there's a lot of work to do there. As I mentioned, I offer you this gradient descent result just as kind of a proof of concept that I think you really can reason about parameter tuning in a machine learning context. I see no reason why you couldn't have more general results of this form. And then finally, I propose for you sort of a non-standard way to measure the simplicity of a class of algorithms. Okay? Something which usually we would leave undefined in a textbook or a research paper. So the pseudodimension provides you with some notion of how simple the class is. Of course, we have a lot of other measures of the complexity of algorithms and problems, and I can't help but wonder if there's any non-trivial connections between these different ways of measuring complexity. So I'll leave it there. Thanks very much.